Hello and welcome back to the project number 2 of this playlist, that is deep learning projects. Today the dataset that I have chosen is rather a famous dataset that you guys must be aware of, that is CIFAR-10 dataset. If you are not already aware of it, don't worry, we'll be going through step by step through all the process. Just keep this in mind, although this dataset is quite famous. However, the technique that I'll be using for this particular project, it is going to be rather advanced, right? So don't think that it is going to be just yet another project that you must have seen elsewhere. It is going to be completely advanced level project of creating neural network. And yet another thing, the last video, it was the project that we did was using the PyTorch library. Today I'll be using TensorFlow library, that is yet another library that you can use. So with that in mind, let us get started and start off with the project. So here I am in my Google Colab notebook. Now before starting with the project, right away let us see the dataset. So the CIFAR-10 dataset, it is actually a well established benchmark in the field of machine learning and deep learning, specifically designed for image classification. It contains about 60,000 images, as you can see here, and they are colored images. Thereby you have 3 color channels, that is RGB, and the dataset, it is having 10 classes, right? So those classes are all of them over here, that is airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. So each class, they contain equal distribution, that is about 6,000 images from the image total image count, and obviously when you are putting 50,000 as your training images, so in each of the classes 5,000 of those images will be in the training set and 1,000 in the testing set. I'm talking about per class here. So our objective is very clear. We have to familiarize ourselves with this CIFAR-10 dataset, visually maybe inspect sample images from various classes to understand the data distribution. Then we are going to be normalizing the pixel values of the images to enhance model training efficiency. Maybe convert the image labels into a one-hot encoded format suitable for classification task. Then we'll also implement the dot argumentation technique to kind of increase the variability of the data and improve the model generalization. Then obviously we'll go to the designing of the CNN that is catering to this CIFAR-10 dataset using Keras framework. Then of course comes the training part, that is training the CNN using the prepared dataset, and then we'll see if there are some more analysis that we can perform. And at the last, the task is very clear, that is you have to go for the model evaluation. Let us go ahead and right away jump to the Google Colab and see how it all pans out. So I'm going to humbly call this as CIFAR-10 project. All right. So before importing the data, the first step as always is to import all the libraries. So I'm going to start with importing CV2 computer vision. I'm going to import NumPy as NP. I'm going to import you can also import URL lib to basically request any URL that we might be using. We'll import the usual matplotlib.pyplot as plt. Then the training trend split is not required for us because it is already provided to us. So but from Keras dot datasets, I'm going to import CIFAR-10, that is the name of the dataset that we'll be using. Then sklearn dot model selection import trend test split. Then I'm going to import TensorFlow dot Keras dot preprocessing dot image. Then you want to import image data generator. Then from Keras dot utils, I'm going to import to underscore categorical. Then import Keras dot models, import sequential to create the sequential network. Then from this has to be from here, and this then Keras dot models, you have to import dense to make sure that it is the dense network that we'll be using. Then convolutional 2D layer which will be utilizing. Then max pooling 2D. From Keras dot layers, I think this should be layers here, and this is going to import dropout, flatten, and batch normalization. Then this is going to be from Keras dot regularizer, import L2 if it is required. I don't think so, but we'll use it. We'll import it for now, but I'm going to import definitely the optimizers. Yeah, I'll be using Adam. Then also I have to import the Keras dot callbacks, import reduce LR on plateau and early stopping, so that we can stop the training of our model if it is not fruitful to us. Then also not required. I'll just run this and make sure that everything is fine here. Okay, so we have imported everything. Now let us train go for the data loading, that is data preparation and exploration. All right, so first import the dataset. I'm going to straight away say x underscore train comma y underscore train. This is going to my training set, and then x test as this, and y test equal to CIFAR-10 dot load data. Okay, so while it gets downloaded, just a very quick note. First is we are actually using CPU as of now, and after coding maybe half of, or at the time of training, basically we'll be using the GPUs, right? So keep that in mind. And one more thing is that people who are not aware, just turn off your AI assistance for this, right? That is going to be very helpful for you. Go to tools and settings, and here AI assistance, just uncheck this box here, okay, because it is going to be very important for you to learn. Otherwise the IntelliSense feature of the Google Colab, it will keep on interfering with whatever you're trying to code. That is not a good way to learn. I highly recommend that you do not use it. Okay, well, I think we have to use trend test split for actually to prepare the validation data, because this is just testing and training set. So I'm going to just import one more thing here from, in fact, I'll not do that over here. I'll just put that somewhere here. I'll say from sklearn dot model selection, you want to import train test split, and then I'm going to say xtrain comma x valid for validation, and ytrain comma y validation is equal to trend underscore test underscore split, and xtrain, it seems I have checked it again. Let me just turn it off very quickly. Not required. Right, so this is xtrain, and then this is ytrain. Test size I'm going to put as maybe 10%, that is 0.1, and random state. So 10% of 50,000 images that we have, thereby the 5,000 it will be in the validation set, and the remaining would be in the training set. So random state, I'm just putting anything. You can put any other random set if you want to. There we go. Let us try to understand the shape of everything that we have got, right? So xtrain comma, sorry, not comma, xtrain dot shape comma ytrain dot shape is this. You see this is 45,000 images of this height and width and this color channel. And then what is ytrain? These are nothing but the label. We'll talk about that in a moment. But if you just see this is, I think if I can show ytrain, you see these are just numbers, and these numbers are nothing but, for example, 0, this 0 stands for the airplane, 1 stands for automobile, 2 is bird, cat is 3, then 4, 5, 6, 7, and all that. So we have to do something about it. We'll make sense of this later on, but let us try to see the shape of other things. That is x valid dot shape comma y valid. Oh, it is validation, unfortunately. Let us put this as valid only, just to be consistent. Run this, and yeah, now this is valid here. Valid dot shape. You can see it is having exactly the same thing, right? 4,500 images, and here as well. So why? Because we have set a test size of 10%. The 10% of 50,000 images, which was at the training images, the number of training images that we had at the first place, the 10% of this is always going to be 5,000, right? So sorry, 4,500, and then the remaining would be this here. Okay, so xtrain and ytrain. I think yeah. So this is because, again, since we are choosing a test size of 10%, right? So that would be 4,500. We had 45 images at the first place, apparently, and from that we got this 0.1. Let me run this one more time. This has to be some problem here. So what I'll do is run everything one more time, because what is happening here is basically I've run this twice. So my xtrain got updated, and thereby I'm getting this kind of wrong number here. This should be, I think, 45,000, and this should be 5,000 if my memory serves well. So what I'll do is I'll just run everything one more time. So it will load the dataset again. There we go. So it will it has loaded the dataset again, and then it has done the split again, and thereby I'm getting 45,000 images rightfully as xtrain and ytrain, and then 5,000 remaining one, they are the validation set. How about the training set? So I'll say x test dot shape. It is the 10,000 images that we had at the first place. Okay, and similarly the y test dot shape is this. Okay, now next is to create the classes. Now for creating the classes, I'm going to take a unique approach. I'll say class underscore names is equal to, I'm going to just copy everything from, if I can find some string here, that would be very helpful. Okay, I don't have any. So let us copy this from, actually I don't have anything. I'll say I'll call this as y train dot classes. Not really. Well, in that case, just copy this one by one and just put that over here, right? Because if I copy this in this manner, it is going to copy the image itself. That is not going to be helpful. So what I have to do basically is create a list of this. So airplane is going to be 0. Okay, and obviously this has to be in a string, right? Then next one, I believe it's automobile. Again, you can type or you can do a copy paste. I'll prefer to type it because that would be better. Bird, then I think cat, if I'm not wrong. So we have bird, cat, deer, dog, frog, horse, ship, and truck. All right, so bird, cat, deer, dog, frog, horse, ship, and truck. Okay, so what I'm trying to do here basically is try to give you an overview of the image that I have loaded. So I'm going to create a figure of this. I'll say for every index in range 64. Why 64? It will be clear in a while. I'm going to create a subplot of 8 by 8 and index plus 1. Then I'm going to say plt dot imshow is x train of that index. Okay, and lastly over here I'll say plt dot show. I'll do one more thing. I'll create a figure at the beginning. So this would be at the beginning itself. I'm drawing a canvas basically. Plt dot figure is going to be fixed size of maybe 15 by 15. Right, run that. There you go. All right, so bunch of things here, very good, but it is not clear. So I'll just fix few of the things here. I'll start with, first of all, I'll say xtix is this empty list. Plt ytix is this empty list, and then I'll say plt dot title. I'll put some title for each of the images. Plt dot title, it is going to be class names that I have created for that index, and at index 0 run that. Okay, there's some problem here. Let me fix this. Yeah, class names, just not this. I have to put y train here, because I'm talking about the corresponding y train that I'm trying to plot over here, right? So I'm plotting the X trend, and the corresponding Y trend, I'm going to put that in the label. And this would be, now if I run this, there we go, quite well, right? So you can see that I'm having this truck here, then horse, then ship, this cat, frog, truck, cat, airplane, dog, and so on and so forth. So this is, again, it is coming from the training set that we got. Now you run this as many times as you want if you want to. Okay, just run this, and every time you can display this image, right? Now here, these are some of the images that I got from the the training set. Now next step, what I'm going to do is I'm going to do the data processing. Data pre-processing rather. In data pre-processing phase, we basically undertake preparatory measures to ensure that our dataset is, aptly prepared for modeling process, and that basically includes three things, right? And it can be more than that as well, but I'll be taking these three things into consideration. That is normalization of images. Second would be one hot encoding of labels. And third is data augmentation. So first step right away is to normalize the data. I'm going to convert all the pixel values to the some sort of number, the floating 32 type number, and then normalize them by subtracting the mean and dividing by the standard deviation of the training set. That enhances the model's training efficiency and effectiveness. So what I'm going to do, well, this is under normalization. So this is normalization, and that is going to have first converting pixel values to float 32. So let's say xtrain dot s type would be float 32, and I'll just copy this particular part. I'll copy this as it is and make some changes. In fact, I'll put this over here. Xtrain here is equal to this, and then I'll copy this and then make the changes. So this is copy, then paste. This is test. This is also test. Then this is valid, and this also is valid. So this is converting pixels value to float 32, and then I'm going to calculate. You can use any other library as well to do this, but I'm taking the conventional method, that is by calculating the mean and standard deviation myself of the training images. So this is going to be mean equal to np dot mean x underscore training set, and standard deviation is equal to np dot standard deviation x underscore train. Then I'm going to take x underscore train and say that x train minus mean, and this is going to be divided by standard deviation plus some very tiny number, maybe 0.00001. The reason for this is to prevent the addition, sorry, prevent the division by 0. That should not happen. That is why we are just adding this extra number here. So x train is this, then this is x test, this is also x test, and same goes one more time for validation set. This is valid, and this is also valid. This is I think there's a typo here. This is S type, by the way. That is why I'm getting the error. There you go. Run this. There you go. Right. So this, what we have done basically is we have normalized the data. Okay. Next step is to do the one hot encoding. Okay, I'm going to convert the class labels to one hot vectors to transform the categorical labels into a format that is suitable for multi-class classification by neural network. So all I have to do is take my Y train, which by the way happens to be all this number, and I have to convert this to categorical and comma 10. Run that. There you go. So now you can see that we have converted that into an array, two-dimensional array, which I'm going to assign to Y train. Now take this entire thing, and this is valid, this is also valid, and now if you're not aware of encoding, that is one hot encoding, it is nothing but kind of putting all the categories into 0 and 1 basically, right? It is like a signal that whether it's a truck is a truck or not a truck. So one means it is a truck, right? Thereby that is the first one at the that I'm getting is, sorry about this, the first one that I'm getting over here, this is telling me that it's a truck. Now maybe this one over here, that is third from the last, it is horse, and so on and so forth, right? So this is the job of one hot encoding. If you're not aware of it, please find out. So this is a white test here that I have to finish doing. So this is one hot encoding of the labels. Next is to do the data augmentation. Alright, so now what I'm going to do is I'm going to implement the data augmentation to kind of artificially expand the size of the training set by creating modified version of the images. Maybe things like rotation, shifts, flips, shearing, intensity changes, and introduce those small variations to existing data, thereby creating many more samples to learn from. Again, the choice of data augmentation often depends on the special characteristics of the dataset and the problem that we are trying to solve. This particular dataset, it is comprising of very small color images of just 32 by 32 size. So given the nature of the augmentation, I'll be doing some sort of rotation, maybe around 15 degree, then maybe height and width changes of something, maybe we can change by about 20% of the height and the width respectively of the images. Now again, since the images are small, the large shifts might not might be basically it might put the object outside of the images. Then maybe we'll do some horizontal flip, because it is a sensible choice for this dataset, because many images, the object of the interest remains the same when flipped horizontal. For example, a flipped image of the car is still going to be car. You're going to be classifying that as a car only. Then maybe some zooming. I'll zoom in by about maybe 10%. That can help our model generalize better. Maybe some brightness and all that, we can deal with that as well. Anyway, let us go ahead and do that. So I'm going to say data generator is going to have image data generator. Now you can see this, there are just so many things over here, so many things that I've discussed: horizontal flip, vertical flip, being false and true and all that. So let us take some of the things. So I'll take the rotation range is 15 degree, and what I'm doing basically is rotate the images by up to 15 degree. Not all the images are rotated by 15 degrees. Some would be maybe one would be maybe 5 degree, then other would be 5.2 degree, then maybe some other 9 degree, and so on and so forth. So this is rotation of the images. Then width shift range is 0.12. This is to shift images horizontally by up to 12% of what? Of width. Width means width, right? So width of the images. Similarly, I'll have the height, and I'm not going into description, but this is height shift range is equal to 0.12. Then I'll say horizontal flip is true. Maybe if you want, you can do vertical flip as well. I'll try to zoom in. Zoom range is about 10%, 0.1. Then this one, you can see the brightness here is somewhere, yeah, brightness range. Okay, so I'll change the brightness up to maybe 10%. So I'll say brightness range is going to be from maybe 10% down and 10% up, 0.1 to 1.1. Okay, so changing the brightness by up to 10%, again both down and below. Then this is shear range. Shear range is nothing but the shear intensity. This, so I'm just explaining the part which is I feel requires the explanation. This is nothing but shear angle in anti-clockwise direction, and just to be clear, this is in degree. And then channel shift intensity as well. Channel shift range is 0.1. Okay, I got an error. Shear range, yeah, it just requires a comma here, and this requires a range. There you go. Alright, so when I run this code, we are setting a pipeline for pre-processing the image during model training. Remember this, we have not still augmented the image. This is just instance that we have created that we are going to be used during will be using during the model training. Because this generator applies a series of this random transformation that you have defined to the image each time there loaded into the model for training. Each time an epoch is run during model training, this random transformation will create different variations of the original image. Right now, let us go ahead and define the model architecture. Right. So the model architecture that I am going to define is inspired from VGG16 network. That is, it contains multiple convolutional layer followed by max pooling and dropout layer, and finally a fully connected layer for classification. While not adapting advanced module like residuals or inceptions, the one that I'm going to design is going to be simpler. I'll ensure that there are fewer parameter and a more straightforward architecture, but I'll try to make it more computationally efficient. Now let us start with what I'm trying to do here. I'm going to start with initializing the model. Model is sequential that we have imported. Then I'm going to set a weight decay. Weight decay is about 0.001. This is for what? Weight decay for L2 regularization. Right. Then I'm going to add the model. I'll say model dot add. It is going to have filter as 32. Okay, so the network begins with a pair of convolutional 2D layer. Pair means I'll be adding one more layer here, and then it will have batch normalization, which accelerates the training and provides some sort of regularization that can help us in preventing the overfitting. Then I'm going to say kernel size is equal to 3 by 3. Padding is, I'll keep it as same. Activation function, activation is equal to relu, and I'll say kernel underscore regularizer equal to L2, then the weight decay that I have defined earlier. Right, then it is going to have the shape that is going to be basically the input shape that I have. Input shape is equal to xtrain dot shape. Grab me everything from 1 onward. Let me run this if everything is well. There's some problem here. This is filter is 32, which looks okay to me. Yeah, filters, by the way, filters. Okay. Oh, all right. So what we have missed basically is we have used the convolutional 2D layer, right? We have missed convolutional 2D here, and this entire thing will go into the parenthesis, and at the end you will have two parentheses, closing parenthesis. And here as well there is some problem in L2 weight decay. This is a regularizer. Okay, there's some problem here. Actually we have to remove this one parenthesis from this side, and now this should work, hopefully. Yeah, There we go. So we have created this. Now this is a long thing. So what I'll do is I'll add one batch normalization one more time. This is model dot add batch normalization. Then I'll take this one more time. I'll copy this, and here I'll paste one more time. Then this entire thing is, again, this is the second convolution layer similar to the first, so I don't have to change anything. Then I'm going to add the pooling layer, right? So I'm going to add first max pooling layer with pool size of 2 by 2. So I'll say model dot add, then max pooling 2D. It is going to say pool size as 2 by 2. Then add dropout layer with 0.2 dropout rate. So I'll say model dot add dropout, then rate is equal to 0.2. Then I'm going to add the third and fourth convolutional layers, and this time I'll include 64 filters. So what I'm going to do again is I'm going to copy these two things, right, and paste it over here, and then make some changes. First change is obviously this is 64. I'll keep the kernel same. There's no point of changing the kernel. Padding is going to remain the same. Activation is going to remain the same. Kernel, regular, everything is going to stay the same. Just one change here. I do not actually want the input shape here. So I'll have to remove this. And I'll remove this from here as well. And here as well, because this again is not the input layer. All right, there we go. So batch normalization. Then next, again, second max pooling layer, same as this one. Again, I'll copy this, make some changes. This is second max pooling layer, and increase will increase the drop rate to 0.3, right, and pool size it is going to remain the same. Then fifth and sixth pooling layer, I'll copy this, paste here. This time I'm going from 64 to 128. Everything else will remain the same. This is also 128. Again, then I'll increase the drop rate to 0.4. Okay, this is second pooling layer, thereby this is third, and this is going to be size 2 by 2, and drop rate would be 0.4. Okay, seventh and eighth pooling layer, copy this and put it over here. This is going to go to 256 filters and 256 filters here. Then this is going to be one more max pooling layer, that is going to be the fourth max pooling layer. This is fourth max pooling layer, and it will have a drop rate of 0.5. Then that's it, I think, right? Then I'm going to flatten out, right? Because this is going to be the raw output, I'll have to flatten out the tensor output. How you're going to do that? From the previous layer, how you're going to do that is model dot add flatten. All right, then you're going to add a fully connected layer with softmax function. Okay, what is the job of this? To output the class probabilities, right? So I'm going to say model dot add dense, give me 10 output because 10 are the number of the classes, and activation here is softmax. Hopefully this will work. There you go. Now whatever we have created, let us try to see the architecture of that. So I'll say model dot summary is this. There you go. Alright, so these are the parameter that we got. Now you can see here right away our model consists of 1.13 parameter, out of which 1.29 they are the trainable ones, and non-trainable ones are this much. Let me see one more time if I got everything right. I think there's some problem here. The problem is that when you see this 16, right? So third one is 16, then 2D is 8. Here this should be 64 actually. Everything should be 64. How come it is 32? I'll have to go back and check this one more time. So this is having, let me check this everything one more time. So the yeah, there you can see. So this is 32. This is not good, right? This is 64. Just to be clear, third and fourth layer, it is 64, isn't it? And rest of the thing, this is 128 and 256. Looks okay to me. Let me just run this one more time. Yeah, now it looks better. You can see 64, 64, 128, 120. Everything is fine now, right? So there are whatever this number are, this is the number parameter, and out of this is the trainable parameter. Now this is again relatively compact model, especially when compared to advanced architecture, which often have like tens and even like millions and billions of parameter. Compared to that, we just have this many, which is still just too much in my opinion. Now I'm going to train my neural network. Now training happens, I'll be using a batch size of about 64, and we will run for about 150 epochs or until the early stopping condition is met. Now just to be clear, this is still a very large model. For running this particular cell, I'll be turning on the GPU, and it still is going to take enough time. So let me just run everything, type everything, and then when we go to the explanation part, so I'll say first I'm going to set the batch size. That is going to be batch size, that is going to be 64, right? Then I'm going to say number of epochs, I'm humbly keeping it as 150. Again, when you are, in your free time, you can put this to 300, about 300 epochs. That would be required. But for now, I'm just keeping 150, and I'll say optimizer is equal to Adam, and that is going to have a learning rate of very small 0.0005. Then I'm going to compile the model with this optimizer and the loss function and the metric, that is the accuracy. So model, I'm going to compile, say optimizer is equal to optimizer loss is categorical cross entropy, matrix is accuracy. Then I'm going to add a reduce LR on plateau. What this is going to do is it is going to reduce the learning rate by whatever the factor that we define when the validation does not improve for, again, the number of whatever the number of epochs that you have, right? Basically, if you define 10 consecutive epoch, then it is going to reduce the learning rate by a factor of 0.5, that is, or whatever the factor that we define when the validation loss does not improve over consecutive epoch. So I'll say this is reduce on plateau, monitor, then validation loss, factor is equal to 0.5, patience is 10, again 10 consecutive losses, and minimum learning rate is 0.001. Okay, so this is, again, it's an optional part, but I suggest that you include this, especially if you go back and run this training epoch for 300 or 400 epoch. In that case, this is going to be very, very helpful. We are not going to do it right now because I do not have that much time to train this for 300 epoch, but you can do it at your end. Just put this instead of 150, I'll put a note here, instead of 150, run this for 300 or maybe 400 epochs. Now, next is to add a early stopping callback that is going to it is going to monitor the validation loss and halt the training process when there's not any improvement for a certain number of epochs, ensuring that model does not waste computational resources and time, right? So this is going to be very important as well. I'll say early stopping is equal to early stopping here, and this is monitor equal to validation loss. Patience is, I'm going to put 40, and restore best weights is true, and I'll also put a verbose here, verbose as 1. Again, this restore based weights, it is going to ensure that the model weights are reset to the values from the epoch. It is going to be reset with the best value of the monitored quantity, in this case the validation loss. Then I'm going to fit the model on the training data using the defined batch size, number of epochs, validation data, and everything else. So let us say model dot fit, it is going to say data generator dot flow is going to accept the training dataset, that is xtrain comma ytrain. Batch size is equal to whatever the batch size that we have defined, and epochs is equal to epochs validation data is equal to x valid comma y valid. Okay, then we have callbacks, reduce LR that we have created, and also early stopping that we have created. Again, both of them are optional. This entire parameter that is callbacks, it is optional. And I'll set a verbose as 2 as well. Okay, I think we got it right. Let me check this one more time. Yeah, there's some issue here. This over here, this should be somewhere here. And then rest of things is fine. At this point, however, you'll have to actually turn on the GPU, because to train this for 150 epoch for this kind of a complex dataset and complex neural network, it is going to take just forever if you do it on CPU. So just turn on the GPU by going to the runtime, go to the change runtime, and just see this T4 GPU. Make sure that you have clicked over here, and then save it. Then you are going to just click on run all so that we can run the entire notebook. Okay, so now it is very late here, but after I think about 2.5 hours, I'm finally able to train my neural network. It was a quite extensive process, really. Yet we just took 150 epoch. So maybe, as I suggested earlier, that will have to go about 300 to 400 epoch. You guys will have to train much longer than just maybe 2 to 3 hours. Anyway, let us see what my neural network is trying to tell me. Let us proceed with the findings of our neural network. Okay, so you can see here that I have got a accuracy of about 90% on my validation data set, right? So that's a good sign actually. But and you can see that we started from the very quite less. In fact, we started at about 45 to 54%, and then we improved up to 90%. Now here you can also see that we have gone only for 150 epoch, and perhaps this particular epoch 149 was the best performing training epoch. Anyway, let us try to visualize what we got. I'm going to generate few plots to visualize the training and validation losses, and maybe try to see the evolution of both losses and accuracy. Alright, so I'm going to plot two things. I'll first set the figure size. This is fixed size is 15 by 6, and then I'm going to plot the training and validation loss and training and validation accuracy. So this is plt dot subplot. It is going to be row 1 column 2, and in that first image, and there I'm going to plot model dot history then loss, and I'll label this as train loss. Also color code this to blue maybe. Similarly, I'll try to get the validation losses as well. I'll just make some changes. There we go. this is going to be not loss but validation underscore loss, and similarly this is validation loss. Color is red in this case, and I'll say plt dot legend is then title is loss evolution. Okay, anyway, let us copy this, paste it over here, and this is figure number 2, and this is no longer a loss but accuracy. Let me copy this, put it over here, here, and here, and here as well. This is the accuracy. And lastly, I'll just put a plt.show to have the image. Okay, I'll just kind of zoom out a bit. Yeah, so you can see that this is the plot that I'm getting. Based on this, it is quite clear that the model is performing well without any particular signs of overfitting. The conclusion is also supported by the close alignment of the training and validation accuracy, and also the loss values throughout the training process. The gap between the training and the validation accuracy remains, it's almost minimal. You can see it is about maybe 10%, right? So the model is able to generalize well on the unseen data. Similarly, the model's loss on validation data follows closely to the training loss, reinforcing the kind of the assertion of a good generalization. Therefore, the model appears to be well regularized and not overfitting to the training data. Now I'm going to evaluate the optimal model on the test data, because remember, this is just what we have done is basically on the training set and the validation set. We have to now evaluate the model on the test data. So for that, I'm going to say model dot evaluate is going to take x test and y test, x test and y test here, and verbose I'm putting as 1. This I have to assign to two things: test losses and test accuracy, and I'll just print those two things. I'll say print f literal test accuracy is curly braces test accuracy \n, and then I'll say this is test loss, this is going to be test loss here. Okay, let us run this. The test accuracy is again about 89%, 90%. So with the test accuracy of more than 90% or about 90%, our model is able to demonstrate I would say exceptional performance on unseen data, because remember, the model is only training on a images of 32 by 32 dimensions. So this high accuracy achieved using a relatively compact model as well of about I think 1.8 million parameter, right? It is remarkable. It is very noteworthy. So many advanced architecture employ again tens or even hundreds of millions of parameters to achieve similar or only slightly better result. But the proximity of the test losses and accuracy to their respective training counterpart that we got over here, that signifies that our model is not merely kind of memorizing the training data, but it is genuinely understanding the pattern and effectively generalizing from the training data to unseen data. So it can be inferred that our model, it not only delivers reliable prediction, but also kind of strikes kind of that fine balance between the efficiency and the performance. Okay, now to explore further generalization capability of our model, I'll assess its performance using some third-party image. I'll just Google anything and hopefully try to do something. Remember, these are all the classes that I have. Okay, so let me just Google one thing, that is horse, right? Any horse here, and then I'm going to maybe just take one image. Okay, there are two horses here. This cannot be allowed because our model is only trained for one thing per image, right? One car per image, one horse per image. So definitely it is going to not perform well for me. What I'm going to do is maybe just take this one here. There you go. Just go to this and I'll copy this URL. So this URL, I'll let me just put a heading here first. What I'm trying to do is basically performance on an out of dataset image. So something that I have just taking from my internet. So URL as a variable, I'm putting that over here. I'll say URL library dot URL request dot URL open, and that is going to be the URL that I have given, and I'm going to store this to some repository, and then I'm going to say image is equal to np.asArray, because I have to convert that to array to do anything, whether to feed to the model or to maybe just visualize it. Then I'll say byte array, then repository dot array here, not array, rather read, because I'll just be reading this, and I have to say data type here is the integer, is going to be equal to cv2 dot image decode image comma cv2 dot I'm read, and I'm looking for something unchanged. There we go. Then I have to convert this to BGR to RGB, because remember my CV2 is going to display it takes in the format BGR, and my matplotlib, it is going to take in RGB. So I have to say CV2 dot CV2 color image CV2 dot color underscore BGR to RGB, and that I'm going to assign to image again. So this particular step is nothing but convert the image. It is converting the image from BGR to RGB, basically blue green red to red green blue. Let me tell this. Oh, okay, apparently this is something that we cannot open, so we'll have to look for something else. Let us take some other image. Hopefully I can take this one, right? So copy this, the URL, and put it over here. Run that. Okay, gone through. Let us display the image, whatever we got. So plt dot I'm show is going to be the image, and I'll say plt dot show here. Okay, there you go. So this is the image that I'm getting. Right now, remember this image, it is having some dimension. What that dimension is? Image dot shape. It is this width, this is this height, and this many color channels. Not useful for us because remember my model is trained for a 32 by 32 pixel dataset. So we need to pre-process it in the same way as we did with the training and test data. And basically what I'm trying to do is I'll say image equal to cv2 dot resize image is 32 by 32, right? Then I'm going to normalize the image because remember my model is trained on the normalized images only. So image is going to be image minus mean that I've calculated divided by standard deviation plus some very small number. Remember to avoid the possibility of getting divided by 0. Then I'm going to add an extra dimension. Why? Because the model expects a batch of image, right? So we had a batch of 64, remember? So we do not have any batch here, we just have one image, but that too has to be in the batch, a batch of just one image. Thereby I'll say image is equal to image dot reshape 1 3 2 3 2 3. Okay, so this is the image that I have. Now let us make the prediction. I'll say predict equal to model dot predict and pass in the image here. So this prediction will be a 10 element probability vector. That is, if I say predict and you see this, you can see it is nothing but the probabilities. The prediction here is the 10 element probability vector, and to get the predicted class all I have to do is find the index with the maximum values. I'll say prediction and dot argument max here. There we go. So I'm getting 7, and if you just pass in the class name for this, class names, and this entire thing over here, you can see it is giving me the horse, right? Make it rather professional. I'll say the predicted class, then curly braces, there you go. Right now you can change any other you can take any other URL as well. Maybe if I just say some other classes are deer, right? So deer, let us say, no deer, maybe let us say some sort of bird, because bird can be anything. So let us try to test our model really to its limit. Let us put some random bird and try to get what I'm getting. So I'll put this image here. You can take any other image if you want to. Okay, there we go. So I'll copy this and put it over here. In fact, I'll comment this out. And there we go, the new URL. So this URL happens to be this bird that we have just got, and this is the shape of the image, which I'm going to convert to 32 by 32 by and 3, then predict it. See the result. You can see it is a bird, right? So my model is also predicting as a bird. Now you can put many other image, maybe try to put a rather complex image, that is at your disposal. Okay, so there we go. This is the end of this particular project. It was very complex project, not really that complex, but especially people who are trying to learn convolutional neural network, it was particularly a difficult project for them. So I hope that you have followed along, and yes, the training, it is going to take some time. You have to be patient, and remember the training that I did, it was on GPU, right? So on obviously the GPU that is being provided by the Google Colab. So, and yet it took about 2 to 3 hours to train the model, but it was quite interesting for me as well. With that, it's time for me to put an end to this video, and maybe we'll meet in the next one. Thank you and goodbye.